Hello everyone, my name is Dhruv Bhavna Mangesh Thakre and today I will be presenting the derivation and numerical solutions for 4 key problems in transport phenomena, focusing on momentum and heat transfer in cylindrical systems. And my reference book is Ismail Tashan. So we move ahead with the derivation 1, which is the problem number 9.3 in Ismail Tashan. The question says that when the ratio of radius of the inner pipe to that of the outer pipe is close to unity, a concentric annulus can be neglected. Use this approximation and show that the modifications of equation 9.12.3 and 9.126 for axial flow in concentric annulus with an inner and outer radii of Kr and R respectively lead to the following equations. The equation mentioned in the question are 9.23 is Vz is equal to this equation, and the volumetric flow rate Q naught, which is mentioned in the question to be 9.126, is this equation. So we move ahead with the next step, which is we write the solution. This is the contemporary diagram for it. The inner radius is Kr and the outer radius is R, where K is the ratio of the inner radius and the outer radius. And in the question it is given us that K tends to unity. So the given things are, and the assumptions are, steady state, laminar and incompressible flow in z direction. Steady state direction makes the accumulation 0. So when we write the momentum balance equation at steady state, which we can write as rate of momentum in minus rate of momentum out plus sum of all forces is equal to accumulation, which is 0 at steady state. So rate of momentum in is equal to 2 pi r L tau rz, which is r momentum in z direction at r. This rate comes from shear stress into surface area. Rate of momentum out is equal to 2 pi L into r plus delta r into tau rz, similarly as same as the earlier one, that momentum in in z direction, and the place is here r plus delta r. So pressure force in is equal to 2 pi r delta r into P naught, which is the pressure, and this comes from pressure into cross sectional area. Pressure force out is equal to 2 pi r delta r into PL. Substituting in the above equation, we get this equation E. Also volume of the shell 2 pi L dot del r. This is the elemental shell volume of the elemental shell, and in the cylindrical coordinate system, dividing the whole equation A by this volume, we get this elemental after cutting out all the common terms. So the next step is to now consider delta R tending to 0, which makes the delta R into del R, and dr tau rz by dr is equal to P naught minus PL by L into R. So now integrating the terms, we get the next equation. We can see that there is a constant C1, and now we again integrate divide the R, and by using the Newton's law of viscosity, tau rx is equal to minus mu dvz by dr, and substituting this in the above equation, and we can again integrate to get the velocity profile of this equation, which is equation number 1. As given in equation 1, curvature can be neglected, that is K tends to 1, as we discussed before. Now consider x to be distance from inner wall, and therefore x is equal to r minus kr, where r is the distance from center, kr is greater than kr and less than r. At inner wall, r is equal to kr, at x is equal to 0. At outer wall, r is equal to capital R, x is equal to r into 1 minus k. Boundary conditions: at x is equal to 0, Vz is equal to 0, r is equal to kr inner wall, and at x is equal to r into 1 minus k, Vz is equal to again 0. This is no slip boundary condition. At x is equal to 0, r is equal to kr, Vz is equal to 0. So substituting, we can get a equation C1 and C2 are the unknowns, and we get the two unknown and two equations, equation 2 and equation 3. So we have two equations and two unknown variables, so we can solve for them. Subtracting equation 2 from 3, we get a equation C1 and we get a value of C1. We substitute it in the equation number 3 and we also get the value of C2, which is this quite large. Now substituting C1 and C2 in the velocity profile and we get this large equation. Now moving ahead with, now we can substitute our approximation that k is equal to 1, and by logical condition we can eliminate this term as 1 minus k square will become 1 minus 1 is equal to 0, and ln k is also equal to 0. So 0 by 0 is will be indefinite, and at r equal to and at k equal to 1, Vz should be equal to 1. At Vz should be equal to some finite value. So we can eliminate by it logically, and after solving ahead, we can approximate this term 1 minus k square upon ln 1 by k to 2. We can solve it numerically. So this is approximately 2, and ln r by r can be approximated to 1 minus r by r. And after all these approximations and taking 2 into 1 minus k common, we get the final result which was required. Now we can say that volumetric flow rate Vz into area, means if we go by the verifying the units, unit of velocity Vz is equal to meter per second and area is meter square, so it indirectly becomes meter cube per second. So for elemental area, dA is equal to 2 pi r dx, where x was the distance from the inner shell to the outer shell. So now solving and integrating this, we can also see that x is again substituted as r, x is equal to r minus rk, where if we differentiate it, dx is equal to dr. And upon integrating all these terms, we get a final result by some manipulations in this, taking things common, and after all the stuff, we can get the our final volumetric flow rate equation and volumetric flow rate profile. So this was question number 1. Question number 2 is derivation 2 from the same book, Ismail Dashan, and the problem is 9.7. Here, the rate of generation per unit time volume is sometimes expressed as function of temperature rather than position. Consider the transmission of an electric current through a wire of radius r if some surface temperature is constant at Tr, and the rate of generation per unit volume is given as k is equal to k naught into 1 plus alpha T. Show the governing equation for temperature. The equation number 2, by use the transformation u is equal to 1 plus alpha T and reduce 2 to the form of 4, equation 4, where phi can be given as k naught alpha by small k. Solve equation number 4 to get the equation T plus 1 by alpha upon Tr plus 1 by alpha. So now, so we start from a very elemental shell. Consider a solid where radius r and length L. We take a cylindrical shell of radius r and thickness delta r. Energy in is equal to 2 pi rl dot qr at r. This is conduction. Energy out, again 2 pi r plus delta r L qr plus r delta r plus delta r. Energy generation is equal to 2 pi r delta r L into S, where S is the energy generation per unit volume. Energy balance can be given as energy in minus energy out plus generation is equal to accumulation. At steady state, accumulation is equal to 0. So substituting all the terms, energy in, energy out plus generation equal to 0, we get equation number 1. Again we write the volume of the cylindrical elemental shell to be 2 pi delta r into L. Dividing equation 1 by volume, we get the of elemental shell, we get the next equation, and upon cancelling out the common terms, we get the next equation, which is 1 by delta R into RQR plus RS is equal to RS. And when we assume that delta R tends to 0, our equation becomes differential equation, and 1 by R d by dr RQR is equal to S, which is equal to K. We can assume it because in equation we have used the notation of K instead of S, so we can write it as K. By Fourier's law, QR is equal to minus K dt by dx, and K is equal to K naught 1 plus alpha t. This is given in the question itself. Equation 2 becomes, after substituting both these equations, this complex equation, and to simplify this, we can use the approximation given in question is equal to u is equal to 1 plus alpha t, du by dr is equal to alpha d dt by dr. So we move to the next equation now. So this is the next equation. Upon not integrating, by rearranging, here we also have one more equation given in question, that phi is equal to k naught alpha by kappa, or not kappa, the conductivity, sorry. And after substituting all these equations, we get a second order differential equation. This is the Bessel equation of zero order. General solution for this Bessel equation is this, as we can see, and upon applying the boundary conditions, at R is equal to 0, temperature should be finite, because in the wire itself the temperature will have some finite value, so Y0 cannot tend to minus infinity, so C2 has to be 0. At R is equal to R, temperature is equal to TR, as we had seen in the question, it is given. So upon substituting U of R is equal to 1 plus TR at radius is equal to R, that is the outer surface, and upon solving and substituting again, we get the final result which was required. And now we move to problem number 3. Problem number 3 is now numerical. We have finished with the derivation parts, and so we start with the steady state temperature distribution in a hollow cylinder of inner and outer radii of 50 cm and 80 cm respectively is given by T is equal to 5000 into 4.073 minus 6 r square plus ln r, where T is in degree Celsius and R is in meter. If thermal conductivity is 5 watt per meter Kelvin, find the rate of energy generation per unit volume. Given inner radius Ri is equal to 50 cm, which is equal to 0.5 meter, outer radius 80 cm is equal to 0.8 meters. Thermal conductivity K is equal to watt per meter Kelvin. Now we move to shell balance. We are considering cylindrical coordinate system, and shell balance is equal to, in the heat transfer, rate of heat in minus rate of heat out plus rate of heat generation is equal to rate of heat of accumulation. So at steady state, accumulation is equal to 0, rate of heat in is equal to 2 pi RL into QR, rate of heat out is equal to 2 pi R delta plus R L QR at R plus delta R. Rate of heat generation is equal to 2 pi R delta R L into Q. So upon substituting all this in the shell balance, now we need to divide the whole shell balance by the volume of the elemental shell, which is 2 pi R delta RL, and delta R tends to 0. So we move now again to the mathematical things in this question. Now by using the Fourier's law, QR is equal to minus K dt by dr, which we substitute in the above equation, and upon substitution we get the value of Q, that is minus K by R d by dr R dt by dr. So now we know the equation of T in terms of R. So T is equal to 5000 into 4.073 minus 6 r square plus ln r. So differentiating it with respect to R, we get the final value of R dt by dr. So multiplying the equation by R requirement is R dt by dr, so we will multiply it and we get the result as r dt by dr is equal to 5000 into 1 minus 12 r square. So if we again differentiate it by with respect to r, so d by dr of 5000 1 minus 12 r square, so the term without the r component will be 0, and 5000 into minus 24r, which is equal to almost 1,20,000 r. So the volumetric flow rate can be given as q is equal to minus k by r into this term, which is 1,20,000 r, and which is also equal to 1,20,000 into k. Now the value of k which we saw was 5 watt per meter Kelvin, and that can be substituted again, and we get it to be almost 6 lakh watt per meter cube. So the rate of heat generation per unit volume is 6 lakh 6 into 10 to the power 5 watt per meter cube. So with this we finish up with our 3 problems, and we move to the last problem, which is 9.6 from the same book, Ismail Dashan. Energy generation with a hollow cylinder of inside and outside radii of 60 and 80 centimeter respectively is 10 to the power 6, as we have seen in the last question. If both surfaces are maintained at 55 degrees Celsius and thermal conductivity is 15 watt per meter Kelvin, calculate maximum temperature under steady conditions. Given inner radius to be 0.6 meter, outer radius to be 0.8 meter. So we again do the same thing, that is shell balance. Take a shell in the cylindrical coordinate system. Rate of energy in minus rate of energy out plus rate of generation is equal to accumulation, which is equal to 0 at steady state conditions. Heat in is equal to 2 pi r L into QR at r. Heat out is equal to 2 pi r plus delta r L QR into r plus delta r. Generation is equal to 2 pi r delta r L into Q. So dividing it by the volume of the differential shell or the elemental shell, which is 2 pi delta r L. So we again get the same equation as we have got from the last 2 problems. 1 by r d by dr r QR is equal to Q. So by Fourier's law, QR is equal to minus k dt by dr minus k by r d by dr, and the same thing again integrating. Now it is different that we are integrating the thing, and upon integration we get one of the constants C1, integration constants. Now we can again divide the r in the LHS to the RHS, and so we get the dt by dr equation, and upon we need to once again integrate it. So upon the second integration we get another value C2. So we should have 2 boundary conditions to get C1 and C2. At boundary conditions, in when the T of Ri is equal to Ts and T of R0 is equal to also Ts. So at Ri is equal to 0.6 meter, when you substitute all the values in it, Ts is equal to 55, and we get 2 equations and 2 unknown variables C2 and C3, and upon solving again subtracting second equation from the third, we get this equation, from where we can find out C1. C2 gets cancelled upon subtraction. So again substituting for Rmax, that is location of temperature, maximum temperature, we only need C1. So when we substitute the value of C1 in dt by dr equal to 0, we get this equation. R square becomes C1 into 2 into K by Q, and upon substituting all the terms we get that R is equal to 0.697 meters. So now we also need to find the maximum temperature. So we need to find the term C2. So for C2 we substitute all the terms and rearrange the equation which we had got as the temperature profile, and we get the C2 to be 14341.2. This is the equation. Substitute Rmax back into T of R, which is we substitute it because at Rmax the temperature we will get at the maximum, and upon substituting all the terms we get the maximum temperature to be 389 degrees Celsius. So thank you for watching. This was my submission for the transport phenomena assignment. I hope you liked it. Thank you.